The integrated rate law, 12-5, worksheet, do number 1, which is number 23 from a book. You see, I copied it, photocopied it. And also number 3. Number 3 is kind of a long graphing problem. Now, this is, I will see how far along I can get with this. I would love to be able to get through the whole thing right now in this one lesson, but we'll see how it goes. It's a lot of material. Okay. You need to know that on the AP exam, pretty frequently, like I will say lately it seems like it's almost every year, they ask a problem on kinetics. Now, I think I've told you before, they always ask thermo, but they ask kinetics quite a bit. So what they do is sometimes when they ask a kinetics problem, it's going to be like the one you did before, called the method of initial rates. Oh, actually like this, like the problem we did last time. They give you data, then you write out the rate law. Rate equals k times this to this power, a to the x power, b to the y power, and so forth. Okay, that's one big problem. You see it? That's a full, like that could be a full 15-20 minute problem on the AP. Or the other one they do is called the integrated rate law, and they show you this based on graphs. So you're going to learn a lot about graphs today in this stuff we're doing. Okay, to start off, these are also, well, what we did before, it said were called differential rate laws. I don't think you have to know the word of that, but the others were called differential, what we did before. This is now the integrated rate law. Now, what they do in the integrated rate law is you only find the rate in relative to one reactant. That's how it would go. And so each single reactant might have a zero, a first, or a second order. It might be first order, second order, or zero order. Kind of strange. I don't know if third even exists. And let's see what else I want to tell you. I'll just start to show you. You'll like this, and you'll find this to be probably easier than the other method. The other is not too bad, but this is even easier once you know your graphs. Okay, so here's how I started off with this. I wrote, you should be familiar with these graphs. Okay, integrated rate law. If you graph a line and just say y versus x, okay, and we say, okay, here's a line right there. Or you could draw that right here on your paper. And we'd say, for that line, y equals mx plus b. You've seen that equation before, that y. What that means is, okay, here's my x-axis. And let's put some numbers, 0, 100. And here we'll go from 0y to 10, okay, whatever. It doesn't really matter, you know, like 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, all right, 1. Okay, so 10 by 10 is 0. Okay, so if I take any point x, like 1, 2, 3, 40, and I come up to here, to the graph, and I get, let's just say, well, I guess that should be about 4 also. I don't know. I don't know what it is. We'll call it 4. 40 and 4 ends up being a point. Well, what that tells me is if I know the value of x is 40, for example, and if I know the slope, I multiply the slope times x, then I add it to what was called b, which is called the y-intercept. All right? So it's where the y began. In fact, another way to write this, y equals mx plus y naught. Yo, okay? Yo is where y begins, the initial y mark, and it was 0. Usually it's 0 in a graph, so we don't really have to worry about that. But so if you start out at 0, then you're going to add to 0 for the y. You add to 0 the value of x, which we said was 40, times whatever the slope is, m, and then you add that to it, and that will get you to this point. So it will get you up here and so forth. So don't worry if I'm saying too much about it, but y final, your final y value, if I want to know what this y value is right here, all I need to do is go down here and take my x value, multiply it by the slope, and then add it to 0 in this case, and I'll get that y value right there. Okay, you're just reading a graph. You've heard everybody say something like, you've heard teachers say, well, okay, if x equals 50 or 5, whatever it is, 50, then what would y be? And you come up here and you say, oh, it will be this number. You hit the line and go over to where that was. Okay, I'm saying too much. So y equals mx plus b. Let's think about that for a minute. What a mess. I kind of drew that messy. Okay, now, if the line were to go down, you can just really just scratch. You can just, well, scratch writing. You can just write it down this way. That would mean that y equals negative mx plus b. Or if you want to say y initial, y final, y initial. You'll see why I'm doing that in a minute. Okay, so if it's a negative slope, there'll be a negative number there. If it's positive, then it'll be going up. Okay? That's important to know. So negative m, negative slope. And of course, slope is a change in y or change in x. Now, here we go. It says, using integration, concentrations of reactant are measured over time and graph versus time. The equation y equals mx plus b is rewritten for each order. Now, not everybody teaches it this way. Maybe your book doesn't. But I think this is the best way to learn this, and I'll show you. All right. We've already talked about this in the first lessons. A is just any reactant you want to have in a chemical reaction. Like, we did some that were... Actually, I think we're going to do it again here. Let me see. Oh, no, we might not do NO2. But we did one before that was like NO2. We said two NO2s, okay? And then they bumped into each other to make, N2O4. Or I don't know if we're going to see that forever. So if that were the case, the reactant is NO2. And as time goes by, what happens when you graph? This is the molarity of NO2. Remember, initial molarity is up here. And remember, it looks like this when it goes down. You see a curve. I mentioned that to you as well. Okay, now I just made that up. It can be any reaction, any reactant. But A is a single reactant. And this is how the graph looks when you just graph it as time goes by. Oh my goodness, I'm so sorry that I might have messed up your graph. I didn't realize I got to draw zero order. Okay, typically this is what it looks like. However, there are some reactions, not this one, okay, but some reactions do this. And I am really sorry for putting that. If you drew that, you'll have to draw another one, but I'll show you. If something is zero order, you actually get a straight line going down with a negative slope. If it's called zero order. Zero order means that the chemical, like NO2 or whatever, to the zero power, rate equal. Okay, let me back up. This is true for most most reactants. But the integrated rate law kind of looks at this form. Rate equals K times A to the X power. Okay, so if X is 0, that means that it doesn't even depend on the concentration of A. Like if it's 0, that becomes a 1, so rate will just equal what K says. It doesn't even matter what A is. All right, if that's the case, some reactants will not affect the reaction. I've got paper zero under my feet. Then that's called zero order. So I am so sorry. So sometimes we'll write zero or zero order. That should have been in the first graph, zero order. I didn't label it very good. Well, I did label zero orders have a negative slope. Okay, so the concentration of A versus time is a straight line going down. Now, okay, so what I told you about, we've been doing it this way. Well, that is, you usually get a curve, but not in a zero order, a very rare and a strange reaction. In fact, zero order was never on the AP for like 70 years or something. Then maybe it was like 10, 15 years ago, they suddenly put one, about 10 years ago, I think, they put a zero order, and everybody could be like, oh my goodness, they were really surprised for a lot of reasons. And I'll tell you more about that as we go on. But zero order was on there. Now, here's what I want to show you. I wonder if I should jump ahead on the graphs. I'll just put them each one. All right, zero order. Now, if I wrote, time is just going to be t. And sometimes when I make my t, like I tell in physics, I'll put a little graph, a little hook on it, a little hook at the end of it, because that way you won't mix it up with being a 1 or something, or a 7. You know how you put lines. That definitely does not. That would not be a 1 or a 7. If I read your handwriting, or AP readers read that, they would not think that's a 1 or a 7. So anyway, all right. So here we go. I'm going to make an equation here. Y equals mx plus y o, or y final. Now, what exactly is y final? Let's think about this for a minute. Okay, well, what is y? Y is the concentration of A. So the concentration of A, the final concentration of A, is equal to. Now, there's another little change on this we've got to make because it has a negative slope, so it goes down. Negative, guess what? The slope of that line is K. Aha. X is going to be your T, your time, plus concentration of A initial. Now, this becomes a very important equation that you'll want to memorize. But now, if you can draw a graph, all you got to do is remember zero order. When you graph concentration of A versus time, if you get a straight line with a negative slope, that's zero order. Okay, there it is. And the equation for a zero order process would be A final, concentration of A final is negative KT. K is the rate constant plus concentration of A initial. Okay, that's for zero order. All right, now we'll move on to the next page. Now, there are going to be three really important graphs to remember. This is one of them, okay? Well, maybe four. Okay, then here goes the next graph. And let me take this away because I started giving you that example, and then that is certainly not a zero order one. But anyway, okay, for zero order, you just put concentration versus time, you see it. This is, but when you get a first or second order reaction, you only get curves. So if you have a second order, well, you're going to write this down, but I'm gonna move it somewhere in a moment. Maybe I'll put it over here. If you have a first or second order, then when you graph concentration of A versus time, you're going to get, as we told you, a curve going down. That goes down, and that means that the slope is constantly changing. This is the one that I told you about in the beginning of the chapter, saying that most every reaction, the reactants, they decrease. Well, it's true. Reaction gets slower and slower as time goes by because there's less and less things to react. Well, this one is interesting because notice the reactant doesn't even matter because it's zero order in this one. But for any first or second, if you graph concentration of A versus time, and you're going to graph at some point in this assignment, you're going to get a curve. Okay, well, that won't really help you, but how can I tell apart first and second? So this is going to be first order. I'm going to label this the graph below. So if you're writing these in your notes, since I kind of might have messed you up on that first one, if I should have labeled, well, it is labeled. That was a zero order, should be the line straight down. Okay. Now, if you graph a first or second order, you can write that one here. First or second order, you get concentration of A. I don't know why I did two of them. Oh well, it's the same thing. You just dropped them twice. I mean, I think second's going to be a little bit wider out or something coming out there. But oh well. All right, but for a first order, we're going to go down to the bottom right here, and I'm going to show you the first order. So, if what you do now, let me think of a way. I kind of had to jump to another page to do this, but yeah, I'll take some data on another page for a moment. I'm going to show you something. But let's just say that you graphed A and you had time. Well, just time. So like a graph, watch what I'm going to do for a minute. You don't have to write this down. But time, it's just time 0, then 1,000 seconds. We're going to get back to this one. You're going to see this in a little bit. 1,800 seconds, 2,800 seconds. What happens to the concentration of A? Let's just say it's 0.0100 or 0.00625 or 0.00476. Let's just do three of them. We don't need that many. Okay, now here's the deal. If I were to graph this, and I'm going to graph 0.0, 0.0100, then 1,000, 0.00625, and 1,800, 0.00476. If I graph them, and if I were to get a straight line, I know, hey, that's zero order right off. But let's just say now that I graph them and I get a curve like this, it'd be very obvious. Now you'd need more than 3 points to really see it. But just say you graph all the points, you're like, wow, that is definitely not a line. You know, that is not a line right there. Okay, that would not be a line. Okay, so Now, if you graph something and you got like, remember I mentioned this in another video, but you could get something like that. That could be a line right there. It just maybe some point here messed up, but most of those would pretty much fall straight down. It doesn't really curve a whole lot, because especially that one kind of brings it back down again. So it looks like your line goes like right through there. So that's if I did it with a straight edge, that's a line, okay? But now if I did something like this, where you obviously see them curving out, or it'd probably be a little bit less than that. But anyway, that is definitely not a line right there, okay? Or you might even start up here even. So that would be a curve. Okay, so here we go. If you graph, because you're going to graph later, you're going to graph some points and you get a curve, then here's the first thing you need to do. You're going to take ln. What? ln? That's the natural log of these numbers. So on your calculator, what you'll do is you'll put in, okay, I'm going to take ln of the concentration of A. And when I do that, I'll put 0.0100 ln. And it comes out to be negative 4.605. Now, you don't have to write these down, but you can just listen to me now and you'll see. If you want to, you may. 0.00625. I pushed ln, and it's negative 5.075. And then if I push for this one, 0.00476 ln. Now, some calculators, you'll put ln, then type in the number, then enter, okay? But anyway, 0.0476 ln, negative 5.347. Yeah, I'm just checking my... Or 48 if you want to. It doesn't matter. 348. Okay. Now, why did we find the natural log? Well, here's what happens in the first order. Well, I guess I could have kept that there. Or, let me see. Okay, I'll rewrite it up here. For first or second, remember, concentration versus time gives you a curve. Okay, now, if you have a first order, which is on your paper, it's going to be right here. Integrated rate law, first order. You're going to graph the natural log of A versus time. Oh boy, I'm going to be all the way to the edge there, but it'll work. Natural log of A versus time. And guess what will happen? You get, yay, we get a straight line if it is a first order. So, now, the data I gave you here, we'll get to that in a minute. Yeah, actually, we'll get to that later. I told you that. Don't look at where I got that from. Well, first order, so I'll just put first order. All right, so zero order, first order would be natural log. So again, if A versus time does not give you a straight line, then you say, well, I'm going to take the natural log of every number here, and now I get a straight line. Yay, that will mean it's first order. But what if you take the natural log of A and you graph it, and you don't get and you get a curve or something, you don't get a straight line. Oh no! Well then you do one more thing, and that will be what becomes second order. Then you're going to take the inverse. Okay, you'll take 1 divided by A. Now another way to write that is A to the negative 1 power. So concentration of A. In fact, on your calculator, you might have a button that does that for you. I'll show that to you on the calculator on mine. Let's see if I can find it. That's one neat thing about at least using the online here. Where is that? Oh, no. Is it on my calculator? Oh boy, maybe I don't have it. I thought I did have it. Well, 1 divided by X would do it. Some calculators do it. I guess mine doesn't. I can't find it. That's interesting because I thought, wait, is that 1 over X? Oh, it is. I do have it. Wow, here it is. Look above this little whatever that bracket thing is. Do you see there's a 1 over X? But I have to push Shift and then that to do 1 over X button. Okay, so what are you going to do? I'm going to take 0.0100 and I'm going to push shift and then that button and I get the number 100, and that makes sense. Okay. Now I'm going to put in 0.00625 and I'll push the shift and the 1 over x and I get 160. Then I'll push 0.00476, then shift and 1 over x again, and I get, there it is, 210. I'm just double checking my numbers here. Okay, so this does not give a straight line, let's say, curve. Natural log versus time does not give a straight line. And let's just say it's another curve. I erased that one. So then the last thing you do is 1 over the concentrations. Or they write it as a to the negative 1 also. And if that gives you a straight line, then you know you have second order. So, I'm running out of space here. First order, first order, and then second order. I guess I'm going to just write second order. Well, I can erase the data now. You know where it came from, and you know how I got it, okay? Well, actually, let me just put it down here. I'm going to rewrite it somewhere. I want to tell you one little thing about that. So if I graph a to the negative 1 versus time, and I get... Now, here's the interesting thing about this. When you do an inverse, can you notice when you inverse a number, well, this was 100. That becomes 100. This was a small... Look, here's a larger number, 100, going down smaller, smaller. Remember, as time goes by, smaller, 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 decreases. But here, they're increasing. So that means your line is actually going to be up. It's going to have a positive slope. So if the inverse of a, 1 over a, it can be 1 over a versus time, or just a to the negative 1 versus time, gives you a straight line with a positive slope. That is second order. All right. Now, let me tell you one quick thing, and then I'm going to erase it. I'm going to redraw it and tell you a little more about this. Just one thing to know. So when you look at data, if it's graphed, and what they do on the AP is a lot of times they give you the data already done. You don't have to sit there and do it, okay? But they give you the data, then they give you 3 graphs, and you look at them, and you say they give you this graph, and that graph. Which one? And you got to find which one's a straight line. And when you find it, you say, if it's concentration versus time, it's 0 order. If it's natural log of A versus time, it's a first order. Or if it's the inverse versus time, it's a second order. Okay, now I'm going to tell you one little thing before I go on and show you a little bit more, and that is this. Once you find the straight line, you need to find the slope of the line. And the slope of the line will be K. Remember I showed you that a moment ago? K is the slope of the line. So another way to find K, instead of doing all that math we did in the last lesson, you find the slope. But when you find the slope, be very careful. Because remember, slope is change in y over change in x, right? So that means y2 minus y1 over x2 minus x1. So what you might want to do, and I always tell people this with your data, t is always x. So that right on the data, you might put a little x right there. So that's the x-axis. Now, if this is a straight line, then you say that's my y. So I can use a point like 0, 0.0100, 1800, and this. And I'll get 2 points, y2 minus y1 over x2 minus x1. You ought to see, that's easy to do. You can actually use the data they give you when they give you data. That's another good thing. Now, if this were the straight line, natural log, now that is your y-axis, if that gives you a straight line. And so it will be y2 minus y1 over x2 minus x1. Okay, that's just the slope of that line. That will give you k. And then last of all, if it were a second order process, well, then that is your y-axis. So 210 minus 100 divided by 1800 minus 0. Okay, y2 minus y1. It's always that. That's a quick, little, easy thing before I get into a little bit more with you here. Okay, so remember that little procedure. We're gonna see those numbers again actually later on. But here we go. So here's the big summary, and I'll show you what you should have drawn on these graphs. I guess I kind of abandoned this a little bit. I didn't. I'll go back. I'm going to go back to. All right, there is 0 order. And we said for zero order, right, that's what your zero order equation was. For first order, that means you get a straight line when you take ln of a versus time. And that will give you also a straight line with a negative slope. So if y equals mx plus b, or I'll put negative, negative y yo, whatever. You can just think about that. You don't have to write this down. But your y-axis is now ln of a final equals negative kt plus ln of a initial. Okay. All right. So that is your equation for a zero. That's the equation for a first order. And then for a second order, the equation looks like this. Now, did I give you a place on your notes to put these? Yeah, it was down here. So integrated rate law, natural log of a versus time gives you a straight line with a negative slope. And that's where you could write this equation. Then for 1 over a, for this one, you'll write a line with a positive slope going up. And I don't know why I put 2 of those there. I guess that looks like a misprint down here. The bottom one isn't even needed right here. But 1 over a versus time, if that gives you a positive slope line, that's what I'm going to do right now. So you would draw 1 over a, or a to the negative 1. I guess that might be what I meant to put. I don't know why I did that. I don't usually write it this way, but AP does both. They just one year they'll do it this way, the next year they'll do it with a to the negative 1. Just they just want to switch it up on you, okay? 1 over a versus time looks like that. So now that's going to be, now I actually like to put a to the negative 1 when I write it down because it's easier to write this equation here. It'll be a to the negative 1 final equals positive kt this time plus a to the negative 1 initial. Now, another way to write this would, of course, be 1 over a final equals kt plus 1 over a initial. All right, so here's what happens. All you do is you look at data, then you pick which graph do I need, which graph gives me the line, and then which equation do I need. There they are. You need to memorize these. However, they do give you on the AP formula sheet, they do give you these equations. But there's a twist to it. Look at how they give it to you. Instead of writing it this way, they write it like this. Well, first of all, they don't put the final like I do. This is how they write it on the AP formula sheet, okay? Now, they don't even write the final there, so they write it that way. This one, they'll write ln of a, so notice what I'm doing algebraically to this equation. But it doesn't even matter because it's the same equation, and you don't even need to, rely on their equation. But then make sure you know that this negative kt, and again, that final thing is not written there. And then for this one, they actually do use this version of it, and they put 1 over a minus 1 over a initial equals positive kt. So that's what's written on the AP formula sheet. Now, here is something, a little history lesson, just out of curiosity you might like to hear about AP. As I told you, for like 70 years, 80 years, they never put a zero order on the AP exam. Never. In fact, for all those years, they always gave you this equation for first order and this equation for second order. Then, about 10, 15 years ago, I'm just going to guess, it was in that time, I was teaching then, AP, they put a zero order on it. Or maybe it was right before I started teaching AP. But they put a zero order, and they did not give the equation. How about that? So on the equation sheet, they had this one, and this one. First order, second order. Imagine that year you took the AP exam. First order, second order, that's all they ever asked. And your teacher said to you, hey, they've never asked zero order. They only asked first, second order. You get the AP exam. Here's the first order equation written on the AP exam. Here's the second order on the AP exam. And they ask you a zero order question. So people got pretty mad, and teachers too, about that. And so then what did AP do? Well, they said, I'm sorry you're mad, whatever. Colleges want this too. Then a few years later, they put it again. Okay, like another, right again. They got you back, and they didn't give the equation. But well, now recently, just about, I don't know how many years ago it was, I'll say 5 or 6 years ago, they finally now give you the zero order equation. But they give you this, this, and this. And I tell you, it's better just to know how to make it yourself out of y equals mx plus b. Okay, enough of that. So now we can do a problem. All right, here we go. So, yes, I'm probably going to have to, in fact, let me see how my timer, my personal timer, yeah, I'm going all right. I can do a little bit more here. All right, let's see how far I can go. All right, so that second order would have been written right here. Oh, I put zero order last. I'm sorry. So, all right, integrated rate law, natural log of A, straight line going down. Second order, 1 over A, a positive line going up. I don't even know why that one is there. Then here is zero order, and that's just a straight line going down. I did that one first, and that would have been the last one. But okay, we did that in the first block. Here we go. So here's a problem like they do on the AP. Example A. Butadiene forms its dimer according to the following reaction. 2C4H6 gives you C8H12. By the way, there is something I need to tell you about adding into the equations, and I can tell this problem is going to have it. And I'm going to tell you about that right now. Let me just show it to you real quick. Okay, so I have to write these down again. Well, negative KT, yeah. I'm going to make a change on these equations. You'll see why in a minute. Okay, natural log of A final. Oh, sorry. See, it'd be so much better if I had a bigger chalkboard in a classroom. I would not have erased these. But the moment I erase them, then I'm like, oh, you're going to need them again. Positive KT. Okay. What am I doing? No. Okay. We're going to try to think here. Initial. -1. Okay. Well, here it is. Watch this. This is only something that it happened about 20 years ago in the AP exam. 20 years ago, they asked a question like this. Then, they asked another one about 2 years ago. So, they waited 20 years before they did this again. But watch this. I'm going to put a little N in front of that K. A little orange N and a little N right there. What does that mean? What that N equals the coefficient in the equation, in the balanced equation. In fact, the coefficient, how about this? The coefficient for A in the balanced equation, okay? So, whatever A is, in this case, C4H6, there's a 2 there. Usually, it's only 1, okay? Usually, whenever we do these, they only do it for 1. It's a 1, and it won't work. It won't have to worry about it. But you can remember that the stoichiometry, remember how I showed you how curves were done? That when you draw curves, the curve is based on, I did show you that, right? Yeah. I did. Increase, decrease, but yeah, the curves drawing. The curve, the values curve based on the stoichiometry of the equation. Remember I showed you that? Well, same thing is true here. That 2 needs to be there. So what that means is, when you find the slope of the line, you actually have to divide by what that is. That number is right there. So, if you put a 2 right there, you'll have to divide your answer by 2 to get the answer. That's what we're saying. You'll have to divide it by 2, whatever, to get K. All right, that's all. But now, they asked that a few years ago on the AP, and it had come back after 20 years. It had not been there. They asked it, and they were a little bit lenient if you didn't do that. But my prediction is next time around they won't be so lenient. So that you got to know that, and maybe they won't even do it again for another 20 years. So you might be out of the AP by then. Yeah, hopefully you'll be a long way out of college by then. Okay, so back to this. Here we go. So this is how they've done it along the AP. They say, look at the data. And notice this. They gave you the concentration is going smaller, smaller, smaller as time goes by. And they even gave you the natural log. And they also gave you the inverse. So they did all the math for you. And look at this. They even made the graphs for you. This graph, this graph, this graph. So look at the graphs. 1, 2, 3. Think for a minute. What order is this going to be? Concentration of C4H6 versus time. Natural log of C4H6 versus time. C4H6 to the negative 1 power versus time. Oh, there it is. What is that? That means it's going to be second order. Because, and here's how you write it. And so here it is. Question number 1. What is the order of this reaction with respect to C4H6? And explain why. Okay. Before I do, well, I'm going to do number 1, but I'll tell you, kind of like we did the other calculation problem in the earlier lesson, you kind of write a generic law, rate equals K times C4H6 to the X power. And we don't know what X is. Well, now, if it's second order, now we know, oh, it's 2. So X is going to be 2. We got that. So it is second order. It is second order. Now, here's what they want you to write. Oh, my bad writing. It is second order because, now watch what I'm going to say. You got to say these words. The graph of the graph of C4H6 to the negative 1 power. Or if you want to write 1 over C4H6. Versus time. Okay, watch. The graph of C4H6 to negative 1 versus time. You might even want to write the word time. You don't have to. Versus time. T is okay. Or that one. Okay. Produces or gives a straight line with a positive slope. Now, let me tell you how important this is. That is very important. That is very important. And that is very important. Because a lot of people, when I give quizzes on this and tests, and even on the AP exam, it happens too, I'm sure, they write, it's second order because the graphs gives a straight line. Because the graph gives a straight line. They gave you 3 graphs. 1, 2, 3. The graph gives a straight line. Okay, or it is second order because the graph makes a straight line with a positive slope. You might even say that. You have to say all of those things. Now, if you really are lazy and you really wanted to try to shorten it, you could. Maybe they call this graph A, graph B, graph C. Or you could, on your paper, you're allowed to write A, B, C, and you can say, oh, because graph C produces a straight line with a positive. That's okay, then you knew it. But this is actually the best way. All right, there it is. Question number 1. Number 2, write the rate law for this reaction. Well, the rate law is, and I kind of showed you, C4H6 to the negative 1. K times C4H6 to the negative 1. Rate equals K, C4H6 to the negative 1. There it is. Now, all right, number 3 says, calculate the value of the rate constant for this reaction, specifying the units. Okay, so here we go. Remember I told you you can find the rate constant by doing the slope. So that's what we'll do here. So, I already explained this to you, so this will go kind of quick. So what I'm going to do, and guess what? This is the data I was using. You probably can see there. Actually, I haven't written anything at all. Do I have a red pen? Oh, I do. What a great thing. Okay, I can do it right now. All right, so here's what I'm going to do. I'm just going to circle. So the positive slope was C4 to the negative 1 versus time. So as I told you, I'm going to put for time, that is my x-axis. And C4H6 to the negative 1, that is my y-axis. right there. Make sure you only look at these numbers and only look at those numbers. Don't ignore all these in here. Okay. Now, because they did the math for you. Now, I only want to say an if on that. Okay, so here we go. So, K will equal the slope of the line. Actually, 2 times K equals the slope of the line. Don't forget, because of that little 2 right there in this particular problem. 2 times K equals the slope of the line, of that line we showed you. So, I'm going to write the slope equals, of course, you could write it y2 minus y1, but I'm going to use the last value and the first value for y. So 481 minus minus 100, not 0, divided by 6200 minus 0. Now, if you want to write down that that's, I'm sorry. On the chalkboard, I can do this. It's right, but I like to always write down the formula. C4H6 -1 final minus C, or 2, how about 2, whatever. Yeah, I'll put final. Minus C4H6 -1 initial divided by time final minus time initial. You don't have to write this, but that might help you a little bit. And if you really wanted to, also, if you labeled the data as I wrote, y2 minus y1 over x2 minus x1. You can write that too. You don't have to write any of this at all. You can just write the numbers. I'm just telling you that's where it came from. 481 minus 100 over 6200 minus 0. So let's figure that out. So 481 minus 100 is 381. Why did I need a calculator for that? See, that's what happens. You get so tied to the technology and you forget the obvious. You overlook the obvious. Okay, so 0.0615. Now, 0.0615, 481 minus 1. Just double checking my math. Yeah, 0.0615. Okay, now, so K will equal 2 times K equals that. So 2K, because of the coefficient 2K, because n equals 2. You don't have to say that. 2K equals 0.0615. So K would equal, divide by 2, 0.0307. Okay, but now we have to put in the units. Okay, oh boy. So here we go. Remember, when you write the units, I told you to write down the rate law. Rate equals K times C4H6 to the second power for this one, because it's second order, all right? Did I write that down on my question earlier? I hope I did, yeah. I erased it, but yeah, that was the answer to write the rate law for the reaction. Number 2, it should have been that. I hope I didn't put a -1 there. I can't even remember my mind. I go so quick erasing things. Okay, now what was the rate measured in? Let's look at this question and see. For this one, it says, time is in seconds, and it's in mole per liter. Be very careful. Sometimes they put it in minutes, and maybe one of the homework ones will do that. And so that means it's mole per liter per second, okay? It's in mole per liter per second equals K times, that's just mole per liter, but then we square it. So it'll be, all right, both sides, it becomes, all right, that's, okay, mole, am I going to be able to fit this on the page? On the chalkboard, on the video screen? It's mole to the second over liter to second when you square them. So now I'm going to multiply that by liter second over mole second. Now, there's going to be a big shortcut for some of you. I can think of who some of the people are. Some of you sharp, quick people can do this. You don't have to show this work. You don't. You can just put the unit if you know it. But watch this. So liter is going to cancel out with liter. Liter squared, mole squared, mole squared. So one of these liters will go away. It's liter. And then mole cancels out down there to make it liter mole. So it's going to be, and I left off, sorry, mole per liter per second. Okay, so it's going to be liter making sure I did it right. Mole squared, we'll take away, that becomes mole per liter per second. Yeah, it becomes, take away 1 mole. Wait, I don't know my mind. I know I did it right. Yeah, liter goes canceled out. That liter cancels. The mole on the top, one of those cancels. So it's liter over mole second. That's the unit. Liter, mole, -1, second, -1. Okay, so liters, mole, -1, second, -1. Now, if you wanted to write liter over mole second, that's okay. Now, if you really want to be crazy with this, remember mole per liter is molarity. So you can do inverse molarity second, S -1, if you wanted to. I'll go with that. Liter per mole, -1, second, -1. You can also write liter mole second, or you can write molarity -1, S -1. Okay, so those are all the possibilities. Now, it looks like, I know we got 4 more things to do, and it looks like that I'll have to take here. This will have to be a place where I'll take a little stop. So I'll make a part 2 video when I got time. I gotta run do something else here.